videos, let's quickly refresh our mind about random forests and discuss the differences between random forest and a gradient boosted tree. If you remember, in the previous videos, we talked about random forests and the fact that they use randomization at two levels. The very first one is on training data, and the second one is by choosing random features. They are going to create multiple trees and then use soft voting to create a consensus of all the three trees as the final classification. On the other hand, gradient boosted trees sequentially builds trees such that each tree corrects the mistakes of the previous tree and improves on the predictions. In other words, there is not going to be any randomization performed when we're working with the gradient boosted trees. In the gradient boosting, the trees are very short. In other words, they're very shallow and they are weak, meaning that they do not have a lot of prediction power. However, as they are sequentially added together using a parameter that is called the learning rate, the performance improves significantly, so that at the very end of the gradient boosted, we're going to have a really good prediction power. Let's see how the gradient boosting works using an example. In this example, we have a data set that contains 7 observations and 3 features. As you can see, the features are open-mindedness, whether or not the person is an introvert, and the IQ of the person. And we want to predict the outcome, which is whether or not the person is a cat lover. So again, we're going to have 7 observations, 3 features, and 1 outcome to classify. The very first step is to make an initial prediction. Now, what is the initial prediction? We are just going to use the log odds as a starting point. Now, for those of you who are not familiar with odds, it is defined as the probability that an event will occur divided by the probability that the event will not occur. Now, in our case, the odds of a cat person, or in other words, the odds that an individual is a cat person, is going to be the cat person divided by not a cat person. So in this example, the data set that we had, remember we had 7 observations, there are 4 instances where the person is a cat person. So it's going to be 4/7. That's the probability of being a cat person. And there are 3 instances where the person is not a cat person, so it's going to be 3/7. Therefore, the odds of being a cat person is going to be 4/7 divided by 3/7, and if we simplify it, it's going to be 4/3. And the log odds is going to simply be log of the odds. And here it's going to be log of the 4 divided by 3, which, if you do the calculations, is going to be equal to 0.125. Once you have calculated the log odds of being a cat person, the next step is to turn log odds into a probability. How are we going to do that? You're going to use the logit function. So the way that we turn the log odds into a probability is to use the logit function, which is exponentiate of the log odds divided by 1 plus exponentiate of the log odds. So in this example, because of the fact that the log odds is equal to 0.125, we're going to have e to the power of 0.125 divided by 1 plus e to the power of 125, which if you put it in your calculator, you'd see that it would be equal to 53%. In other words, this 53% is the initial probability that we have predicted for everyone to be a cat person. So it ain't much, but it's honest work. Now, the second step is to calculate the residuals. What is a residual? A residual is the difference between the observed value, or the actual value, and what we have predicted. In this particular example, you are going to have the observed values in terms of probability. So when a person is actually cat person, the probability that that person is a cat person is going to be equal to 1. And when the person is not a cat person, then that probability is going to be 0. Using that, we can easily calculate the residuals as the difference between that observed value, which is either 1 or 0, minus the predicted value, which you just saw was 53% for everybody. So for this first observation, for example, the residual is going to be equal to 1 because he is a cat person, so probability is 1, minus 0.53, which is the initial predicted probability, which is equal to 0.53 for everybody, and it's going to be equal to 0.47. And for the second person, it's going to be 0. Why? Because he is not a cat person, so the probability of him being a cat person, the actual value is going to be 0 minus 0.53, which is going to be negative 0.53. And this is going to be the residuals calculated for everybody. Once you have calculated the residuals, you're going to build a shallow tree that is going to predict the residuals using the features that we had. So again, this is the updated data table that we have, and the very first thing that we're going to cut is going to be based on the IQ. So those observations that have an IQ, say, higher than 120 are all going to be put in this leaf because all of them are cat people. And then among those that have an IQ of less than 120, the second thing that we're going to cut our data set or split our data set is going to be based on their, say, open-mindedness. And we are going to have two observations that are not open-minded. So these two are going to be at this leaf. And then the third group is going to be the people who have a lower than 120 IQ, but are actually open-minded, and that would be this person's that is put into this leaf. So this is a very shallow decision tree that is classifying all the observations into these leaves. The next step would be to transform the values in the leaves into a single output. And note that the leaves values are derived from probabilities. So we cannot simply add them to the log odd values, to the initial log odd value. So we need to have some transformation formula, and this is one of the most commonly used formulas for transformation. At each leaf, you're going to add up all the residuals, put it in the numerator, and then we're going to add the previous probability of each observation multiplied by 1 minus the previous probability of each observation, and then add them up together. Let's see how it works. So this is the tree that we had, and this is the formula that we're going to use. And let's start with the very first, very easiest leaf that only has one observation, and that is containing only this this negative 0.53, which was the predicted residual for that particular observation. So putting in this formula, because we only have one observation, there's not going to be any summation. So it's going to be the residual, which is negative 0.53. And then remember that the probability that we came up was equal to 0.53 for all the observations. So it's going to be 0.53 multiplied by 1 minus 0.53. And if you put in your calculators, you see that the result of this is going to be negative 2.12, which I'm going to put it down here. Now, the next leaf is this guy, and you can see that there are two observations here. So now we're going to actually use this summation. So the residuals are negative 0.53 and negative 0.53 added together. And then the previous probabilities, again, they were all 0.53 multiplied by 1 minus that probability, which was 0.53 added together. And this happens to be, again, negative 2.12 for this particular leaf. And if you do the same kind of calculation for this node, you're going to get 1.88 for which is going to be the transformed output of this final leaf. Now, the next step is to update the predictions by combining the initial predictions that we used, the log odds, with the new tree using the learning rate that we mentioned at the very beginning of this video. So the new log odds is going to be the previous log odds, which was log of 4/3 plus, I'm talking about this particular node, 1.88 multiplied by the learning rate. This 0.1 is the learning rate that I have put here. And there is the 0.1 is the most common learning rate that people use, but you can change it. You could have used 0.5 or 0.9 or whatever, right? So here in this example, I'm using 0.1. If you do this calculation, you would get 0.313. And this is the log odds. Like before, you have to turn this 0.313, which is the log odds, into a probability using the logit function, and you would get 58%. Let me show this with the data table that we had. So this leaf was about this person. If you remember in the previous couple of minutes, if you go back, you would see that this leaf was this person that was put here. And if you can see, is the person that does not have an IQ of over 120. You see that the IQ is 85, but is an open-minded, yes, and that is the person that is the only observation that would fit into this leaf, given the conditions that we have, right? So the initial probability for this person was 0.53. Now, the new log odds for this person is going to be the initial log odd, which was the log of 4/3, plus 0.1, which is the learning rate, multiplied by negative 2.12, which was the transformed outcome of this leaf, as we did in the previous step, and it's going to be equal to negative 0.08. Now, if we turn it into a probability using the logit function, we are going to have 48%. So, so the new probability is going to be 48%. Now, one thing that I want you to notice here is that we are improving, right? Initially, the probability of this person being a cat person was 53%, and now is 48%. Basically, we're downgrading the probability, which is a step towards the right direction because this person is actually not a cat person, right? So the fact that we are reducing the probability of classifying this guy as a cat person is an improvement, right? Now, let's do this one as well. These 4 observations are the ones that are all placed into this leaf, and if we do the new log odds for them, again, it's going to be the previous log odds, which was log of 4/3, plus the learning rate, which is 0.1, multiplied by 1.88. That was the outcome, the transformed outcome for this leaf, which is going to be 0.313. And if you put it in the logistic formula, logit function, you're going to have 58%. So the new probability for these 4 observations is going to be 58%. And if you do it for the other 2 observations, you would see that in that cases, it is also going to be 58%. So this is a new updated probability. The final step is to basically repeat steps 2 through 5, which means that now that we have a new probability, we are going to calculate a new residual. For example, for this first observation, the new residual is going to be 1 minus 0.58, which is going to be 0.42. And again, for this observation, it's going to be 0 minus 0.48, which is going to be minus 0.48 and so forth. So we calculate the residuals for all the observations, and basically we repeat this algorithm until we either reach the maximum number of the allowed trees in our algorithm, or the residuals basically get almost zero, that is when the algorithm will converge and we will stop. Since we were talking about, classifying cats and dogs, I thought this would be an interesting meme for you guys.